Hello, everyone. As the title says, this is Kubernetes for Science Compute. I'm trying to give an overview of what it takes to run applications on a Kubernetes cluster with an emphasis of typical science compute. I have a bunch of lecture slides which will cover maybe a quarter of the time, and then we have a large set of hands-on exercises where you are pretty much on your own. I'm happy to answer questions, and I will provide the access key to our tutorial cluster, but you expected to do most of the stuff on your own. So hope this sets the expectations. And let me start with my first slide set. I can find it, here we go. And yeah, so let's start with some basics. So I'll briefly outline here what how Kubernetes came to be, what are the basic building blocks, a little more detail of what's available, 2 words about users and permissions, and finally how you actually interact with it. So Kubernetes, how did it actually happen to be? Well, originally it was a Google product. They needed something for their own internal use, and it was so successful they decided, well, we may as well give it away and have others contribute to it, so we make it even better. So it ended up being part of Cloud Native Computing Foundation, and that's where you get it these days. Although Google is still developing its own version, but it periodically contributes things back to the Cloud Native Computing Foundation, and the two are compatible. It's open source and has a very large and active development community. And you should be aware that while it was developed by Google, it can be deployed on-prem, and that's what you will be practicing on. But it's also available out of the box from all the major cloud providers, Google, of course, but also Azure, AWS, and Oracle, and others too, I think. Now, another thing you should be aware of is that Kubernetes is container-based. So the containers are the basic building block. And it all started with Docker being a big proponent of container. They're actually moving away from Docker, but all concepts are still there. You may or may not know that there are many standard images available for containers that you can use as they are, but you can create your own too. And finally, a reminder that containers are meant to be stateless. So if you need any state, you will need to keep it outside. Now, what does Kubernetes provide that Docker does not on itself? Well, Docker is great if you have a single node with a single container, but once you have many containers or many nodes, you need some way to manage the whole system. And usually people call that orchestration these days. And Kubernetes advertises themselves as a production quality orchestration system. And that's what it is. It helps you manage a lot of containers on a lot of nodes. Now, why the containers are the basic building block underneath, really what you as a user will see are pods. That's conceptually the smallest thing you will ever see inside Kubernetes. And a pod is really just a set of containers. And having a single container in a pod is okay, but you can have more than one. And why would you want to do that? Well, the nice thing about pods is that it will schedule all the containers inside the pod on the same node, and they can start sharing some of the resources too. So you can have several containers that interact with each other with very little overhead. Now, said that, you should be also aware that a pod is ephemeral, which means if it terminates, for whatever reason, it's gone. there is nothing persistent about it. And if you need any kind of error recovery, you need something on top of it. And in Kubernetes land, this is called controllers. And they will allow you, help you to restart the pod in case of failure, or even help you run many pods that are similar as a single unit. The most popular controller is called deployment, because while a pod is ephemeral, a deployment is persistent. And the deployment will launch the pod that actually run your containers. But if a pod is removed for whatever reason, a new pod will be automatically resubmitted. Moreover, deployment can also manage multiple pods and can even do stuff like horizontal scaling, which is great for something like service applications. Another controller that you will likely encounter when you use Kubernetes is the job controller, and it's effectively an abstraction of bad jobs. A job controller will make sure that the pod completes, which means essentially the container exits with 0 exit code, unless you can tell him to do something else, but this is the default behavior. And we retry up to a certain number of times before giving up, and that's configurable too. So it will transparently handle pod and container failures. For example, if a node that your pod was goes offline, if you had just a pod, it would just say, okay, I'm done. But a job will resubmit it somewhere else and get it there. It can even help you with parallel execution. So if you want to do, for example, a parameter suite, you can submit a single job with hundreds of pods inside, and the job will make sure they all of them run to completion, which is what you would usually expect for something like batch system, what scientific compute is often all about. Just for completion, there are a lot of controllers in Kubernetes, and you can even write your own if you want. And I will not go over the other ones, just so you know they are there. You can Google it up and you'll see. I would just like to point out 2 more, which will not exercise, but you should probably know they're there. There is a stateful set, which is convenient when you want to have predictable pod names and auto-scaling, and the cron job, which is something that we run periodically a pod for you, which can come pretty handy for some applications. So once you have pods and you start up them, you probably want to configure them. And Kubernetes is great in that it has several mechanisms to inject information into pods, so you don't have to cram everything you need inside the image. There are basically 3 different mechanisms. One is the environment variables. There are config maps, which is essentially a list of files, and secrets, which are like config maps, but with a little more security in it. And on top of that, you can also link to external storage, because, as I said, a pod is ephemeral. It doesn't preserve any information. So there are several hooks in Kubernetes that allow you to attach external storage, which can be either local, and you can even have a local ephemeral storage in it, but can be also persistent depending on your Kubernetes cluster configuration. And you can have true distributed file system, which is managed through something called persistent volume claims. We'll see that in more details later. Just don't forget that you can also move data in and out explicitly, which is not actually handled by Kubernetes directly, but you would probably want to do it anyway. A brief word about networking. When you launch a pod, each container gets its own private IP address, which can be used to move data around. And on top of that, you can create services for load balancing, and you can even have wide area network connectivity, depending on what your cluster supports. I'll go more in detail later, but just to give you a taste of what's available. Now, as I said, it's all about orchestration. So we are managing a lot of pods and a lot of nodes. So you need to have some scheduling. And Kubernetes comes with a pretty decent scheduler. It will match pods to the available resources based on CPU, memory, GPU, storage, a lot of stuff. And it has the usual stuff: nodes advertise what's available, pods specify what they require, and then a match is made. There is also a notion of priorities, so that you can have different classes of workloads that will match at different priorities, and it also supports preemption. Again, more details later, just a taste of what's available at this point. Now, in any system that is used for production, you likely want to have some users and permissions. And Kubernetes have several kinds of users. And just so you know, it's all about what APIs inside Kubernetes you can access. It's not so much who owns the resources. And another thing to be aware of, if the permissions inside Kubernetes are mostly set as part of a namespace concept, unless you are an admin, in which case they are cluster-wide, which implies that once you get a user is authorized to use a namespace, pretty much any other user who can use that namespace has the same permissions, which sort of creates a concept of virtual private Kubernetes cluster inside the namespace, but there is relatively little protection among users inside a namespace. This is a little different than what you probably used in the batch system world, so something to be aware of. User-wide, there are also two separate concepts in Kubernetes. You have proper user accounts, which are for humans, and then you have service accounts, which are for processes, which typically run in the pods, but can be also used for automation, for example, from your laptop. And while user accounts are intended to be global and unique, service accounts are typically namespace-based. And just so you know, I'll soon share a configuration file that has a service account, and that's what you will be using during the hands-on session. A couple of words on permissions. We will not exercise them today, and you may never need to use them if you are just, let's say, vanilla batch user. But if you ever want to write any kind of automation, it's good to know they are there, because you will want to use service accounts and you will want to give your automation some permissions. And the permissions works on two purposes. First, you need to create a role which specifies which permissions are granted. And after you have a role, you bind that role that takes you who gets those permissions. And here you have an example of what it looks like. As I said, we will not go too much into detail, just so you have an idea what it is all about, and you can Google it up and or find more detailed tutorials about this topic elsewhere. So that was all about the concepts. Let's go a little more in detail how you actually access Kubernetes. I mentioned before the APIs, and yes, it's all about APIs behind the scenes, but unless you're a hardcore automation developer, you probably don't want to write scripts to access it. You want command line tools. And to do that, you will need to know two things. First, it's how to actually tell Kubernetes what you want. And you will write YAML files or YAML documents for that. And this is both for creating, configuring pods, deployment services, and also if you want detailed information about the system, it will be a YAML document. Now, don't be too scared, because a YAML is quite easy to use, especially to read, but also to write once you know what you're doing. And that's because YAML describes itself as a human-friendly markup language, The only thing to be aware of it that it uses Python-like indentation, unlike other config files. So as long as you have ever used Python and you know to be careful with indentation, it's actually pretty straightforward. And here I have an example, not expecting you to understand what's in there, but it's an actual YAML file, and you see it doesn't seem too complicated. Now, once you know what you want, you need to interact with Kubernetes, and the tool you will most likely use is kubectl, which has all the commands you need to interface with Kubernetes. Unlike many other systems, this one command is all you ever need unless you want to get really fancy, because you can create new objects, which means pods, deployments, whatever. You can see what's there, you can modify them, you can delete them, and there is even an apply, which is a combination of create and update. So I sent this in the email, but if you haven't installed kubectl yet, just fetch it from the link that was in the email. It's a single static binary, no dependencies needed, and you will need a configuration file to access any Kubernetes cluster. In a second, I'll share the config file for our tutorial cluster. And you can use it from anywhere. Your laptop is just as good as any other system. No shared file system or anything is needed. So yep, that's how we will do all the exercises. And that's what I have for the lecture. And we will now move to the hands-on session. So let me post again. Oh, I saw Susan posted the link there, but let me do it again just in case. So all the material is in the hands-on session. And actually, let me share with Zoom so it gets recorded. Share screen. So all the material is in the hands-on session in GitHub, and all the hands-on material is in this subdirectory. I'll post it again. Chat. So hands-on, it's here, and it's meant to be pretty much copy and paste. So you can go in here and do all the steps. So let me share now the configuration file, because you cannot do anything without that. So copy the link. So I just posted the configuration file inside the chat. Download it, and if you are on Linux, just put it in config. If it's any other system, look what the instructions say for, well, Linux and Mac OS, both its home kubectl, like, yeah. So let me share again this one. It may be easier, but it's in the inside the hands-on. So yeah, download that the config file and put it in this directory on either Linux or macOS. I never actually use it on Windows, so I'm not exactly sure where that goes, but it should be something very similar. And I'm pretty sure it's explained here in the install kubectl for Windows, how to do it. Let's see what it say. Oh, What is the config? It should tell you what is the config, shouldn't it? Well, if anybody has problems finding out how to do it, post in the chat to figure it out. I hope most of you are macOS, which is easy, or Linux. So as I said, you are mostly on your own. I'll answer questions, but yeah, the main idea here is that you do the exercises, and we'll resume in about half an hour with the next hands-on section lecture, which will be again a couple of minutes, and then we'll go to the next hands-on session. That's how it will be for the rest of the morning. Lecture, hands-on, lecture, hands-on. So yeah, don't worry if you haven't finished all the hands-on from the previous session. We will have time to continue later. Let's now move on and talk a little more in detail of some of the things you can do in Kubernetes. So let's restate that Kubernetes is container-based. So the containers are the basic building block, and there are many standard images that you can use out of the box, but you can also build your own. Okay. Now, yeah, so there are container images, but how do you decide which one to use? What image should you use? And maybe the better question is, as a starter, is where are those images coming from to start with? Well, by default, they come from Docker Hub, but you can also provide an arbitrary URL too. And if anyone here has never seen Docker Hub, is just a Docker image hosting site. And most important software projects have a ready-to-use image there. And here is just a snapshot of what you can find there. But really, there are thousands of different images for all kinds of applications already packaged and ready to use. All you need to do is get them. Just be aware that most of the images are versioned by using so-called tags. So you, apart from picking the image name, you also want to pick usually a tag. And if you don't say anything, the default is latest, which may be fine if you do anything on your own, but it's usually not a good idea for if you pick something from other people, because they can change whatever you are downloading under your feet. And you have already used that. The first pod you launched was using a CentOS image. So it is a basic CentOS, and we said we want the CentOS 8 tag. And that's what it did. It was pulled from Docker Hub behind the scenes, and you end it in a CentOS image. You could have picked any other one, and you would have gotten that. Now, having all the standard images is great, but what do you do if the image is not a perfect match? For example, you built your own software. Well, what I don't want just the OS, I want actually to run my software. Or the image has almost everything, but I need some additional libraries. How do we do that? So as you can imagine, customizing the images is quite common. And really, you have two options here when it comes to that. You either inject files into the pod at runtime, just in time, or you build a completely custom image, so it has everything it has, and you build it once, and it's ready to be used. Let's start with the first one, and I showed this slide before. It's essentially configuration management. You want to customize what your pod look like, starting from a basic image that you pulled from Docker Hub or somewhere else. And as I mentioned before, you really have three options. You either inject environment variables, you use config max, or you do secrets. And I'll go over all three of them now. Let's start with config maps, which are the most useful. And while the name may not be obvious what that means, it's really a config map is a collection of files. You create a config map object ahead of time. You put a bunch of files in it, and then you can get any files in those config maps from any pod that you launch. And those files can be mapped pretty much anywhere inside your pod. It's your pick where you want to put them. And another nice thing about config maps is that you can map the whole config map as a directory inside the pod. So you could have potentially hundreds of thousands of files in a config map and map them inside the pod with a single command. I would not really recommend that, but it's an option. And they are not, even though the name implies that it's just for configuration files, you can put anything you want in there. You can put executables, library, whatever you want, and they would be mounted inside your pod. Now here I have a quick example of how you do that. You first define where you want, which config file to use, what files to get up, and then you mount it wherever you want. You will have a chance to do that in the hands-on session, so I'll just briefly go over it. The other option, as I said, is environment variables. And environment variables are definitely easier to use because you don't need to create an environment variable object. You just list the environment variables you want defined inside your pod and just use them. Why would you do that? Well, you probably have some kind of script or executable that can use those config files, those environment variables. And it's either in the pre-built image, or you can inject the script you want or the config file you want to use the environment variables in through a config maps. So environment variables and config maps all often go hand in hand. And here we have an example, and it's actually from the hands-on session. We inject the script, and this script then use an environment variable to do what we want it to do. Okay. And finally, as I mentioned before, there are secrets. Because some information are just more sensitive, like passwords or security tokens. You want them to be a little more protected than standard config maps. So the secret object provides some additional protection. You cannot see what's inside a secret object with kubectl. That said, once it's mapped inside a pod, you can still access it. So the protection is somewhat limited, but it's still good practice to use secrets whenever appropriate, because it does provide a little bit of protection compared to config maps. And apart from that, they are very similar to config maps. Now, that's if you want to inject stuff at runtimes. But sometimes the amount of change you need from any standard image that you have is just too much. Or you want to use some complex packaging. For example, if you want to install a bunch of RPMs, you don't want to try to unpack the RPM and inject in config map. That would be a nightmare. So instead, it's probably better to create a custom image where you can actually get all the software in the right way installed in the image itself. So how do we go about creating an image? You can use the standard Docker image building procedure. If you've ever done that, you probably know what it looks like. If you don't, there is something called a Docker file. It's a text file where you describe what the image should look like. You almost always start from an existing image, and then you build on top of it. So in this example, we start with NVIDIA CUDA image, and then do a bunch of yum installs. And this way, you get all the libraries that you are interested in, assuming those were the files you were interested in. But you don't have to stop by just doing yum installs. For starters, you can run any command you want, but you can also add files and set environment variables. And for example, you have your own software that you built locally, you can just inject it there, or you create configuration files, you set in there, you put default environments, and it will work. Now, the Docker file is not the end of it, because the Docker file is just a text file. You now need to, let's say, compile it. And that's, or like they call it, you need to build the actual image out of the Docker file. And then put it in a place where Kubernetes can fetch it, typically Docker Hub, but you can put it in a private repository too, if you have one. And there are many options that are available to build the image. You can install Docker on your laptop and do it there. You may have a continuous integration system like GitLab to do that. Or you can even do it through the Docker Hub, because they offer a service that allows you to build your Docker files into images. Essentially, you need to put the Docker file and any dependent files in GitHub, and then you build it. Just be aware that this is a premium feature, and you will have to pay for it if you do it. It's not that expensive. I think they charge like $5 a month. Not free, but not terribly expensive. But if you have something at your institution that does it for you, definitely use it. And if you do it very often, maybe you just want to do it on your laptop or something like that. I will not go in details how to do it. Just want to make you aware that that's something you will need to do if you want to build your own custom images. And that's all I have for the lecture. And we can go back to our hands-on. I would recommend you go back to you start the next session if at all possible. Although if you are really behind on the first one, it's okay for you to try to do at least one or two sessions there, because you want to understand the basics. But yeah, here is the second hands-on. I'll post it again in the chat. Yeah, it's same location, just different file. And yeah, just follow along like you have been doing before. And the idea of this hands-on session is to exercise a little more the customization of the pods. Before we go to the scheduled session, I want to show you something else. So here, I just want to point out that whatever we are doing on our Kubernetes cluster, it's not too specific. So here you see I have Google Kubernetes. It's the Kubernetes engine. This is the cluster page. I have a cluster here that happens to be for IceCube, but doesn't matter. And I have some nodes that are there and stuff like that. I can do the usual commands you have done before. I just created a YAML that is identical from the first hands-on. I can create it just the same way. Take a second and it will start. So just want to point out that all the exercises should work, or most of them should work on any Kubernetes cluster. Doesn't matter if it is on-prem, remote, or your toy. Minikube cluster. There are a couple of exercises that are a little more specific to Nautilus because some details do change, but most of them should run anywhere. So that's just a quick show that you can do the same things in the clouds if you want. And let's now go to the next slide show, which is about storage. Share screen. Here we go. So, storage. As I mentioned before, and as you may have already experienced, it's that all the containers are stateless. So after whatever you make change, if you made any changes inside the container, by the time the pod is gone, you lost it. So what do you do about it? You may or may not need the persistence. And if you don't, what you have been doing so far was the right thing. And you probably have noticed that storage inside you have storage inside the container. All or most of the areas are writable on most nodes. And so you can actually write stuff straight into the container. One of the exercises says to do yum install, which will update the same space that the image is in. So you already know that you can actually write inside the container. It's ephemeral, which means next time you start the pod, it will not be there anymore, but you can do that. You also have the RAM disk. I think it's what it is, MNT shared or something like that, where you can write. It's available typically everywhere. But you can also have an explicit ephemeral partition if you want. It's called empty dir volume, and you can size it the way you need. And why would you even consider doing that? Well, there are a couple of reasons. One is, in case your image is not writable, you will need that. But even if it is, remember that you are working with pods. And pods is a set of containers. It can be more than one container. And if it is more than one container, you can share an explicit ephemeral partition between all the pods. So all the containers in the pod. So all the containers can actually share a file system, which is a local, ephemeral, and fast. So you can run different things in different containers, but still maintain a shared file system for them. Doesn't need to be ephemeral, but it can be. But you're probably more interested in proper persistent storage because most of the time when you do run some applications because you either want to consume or produce some data and you don't want to just do toy stuff. And as I mentioned in the beginning, you can either mount local storage or proper shared file system. And we will go a little bit here on how you do that. Again, a reminder, direct access to any external storage is always an option, but it's not directly managed by Kubernetes. So how do you mount external storage? Well, first you need to pick the volume to mount. You may be able to create it at pod creation time. If it's an ephemeral one, you just say, I need a partition, and that will happen automatically for you. But if it is persistent, you need to first have a location that will last for way longer than your pod will. And this is usually called the persistent volume claim. And once you have that volume, you can actually mount it inside the container, similarly to what you have done with config maps. And again, any directory that works for you, it's fine. It's your pod, your compute. And there are very few limits on what you can do there. So here is an example of how you mount an ephemeral partition. You just say, well, I need an ephemeral partition, and I call it my data, and it's of type empty dir. You actually can customize it a little more, but Google that if you're interested in more details. But after you have done that, you can say, okay, that ephemeral partition should be mounted in that directory. Done, and it will happen for you. Now, if you want persistent storage, well, you have to find a storage solution that will actually persist. And the Kubernetes software itself supports many different kinds of persistent storage solutions. Now, of course, one thing it's software support, the other thing is the hardware to back it up. So most clusters will not support all of them. They will likely support a couple if you're if you're lucky. So what exactly you will be able to use depends heavily on what kind of hardware is your cluster running on. So in our tutorial cluster, we have a Ceph file system, which is managed by Rook. And it comes in 3 flavors. That is the Ceph-FS, which is a proper distributed POSIX file system. And as any proper distributed POSIX file system can be shared between many pods. There is Rook Block, which allows you to allocate some of the storage as a block device, and then you do whatever you want with it. If it's a database, probably will use raw access. You can format it as a normal POSIX file system, but it will be limited. You will only be able to mount it in a single pod because it's a block device that you can assign to one pod at a time. And finally, Ceph also has an S3 compatible API, essentially object storage. It's not managed directly by Kubernetes, but it is there if you want to use it to explicitly move data in and out. As you know, object storage is great if you have lots and lots of objects to move around. But we will mostly stick with Ceph-FS, which is the distributed file system. Here is how you request persistent storage in our cluster, and we will do it in the hands-on exercise. Essentially says, I want a Ceph-FS partition of a specific size, and I'm happy to mount it in many pods, and this is its name, and it will be created for you. And then you just need to mount it. You see, it's almost identical to what we had for emptydir, but instead of saying emptydir, it said, this is my persistent volume claim that I have created and will store my data. As simple as that. Now, that's for when you want to stay inside the Kubernetes cluster. What do you do if you need to get data in and out of the cluster, which eventually you will want to, right? Kubernetes per se has very limited data movement capabilities. Since there is no shared file system, you will, between the cluster and your submit machine, you cannot rely on that. So how do you get data in and out? Well, Kubernetes does support something called kubectl-cp, which is conceptually similar to what SCP is in if you use SSH. However, it's not a direct point-to-point file transfer. It actually gets routed through a Kubernetes API server. And as such, it's very slow and can easily overload the Kubernetes cluster if you do it too often. So while it is good enough for testing and debugging, and you should definitely be aware of it, you should not use it for anything big or on a regular basis. So treat it as a last resource for debugging if everything else fails. Oops. So you should definitely plan on using third-party data movement tools inside your containers to do all your file transfers. You can use any combination of wget, gridftp, Globus, S3, X2D, you name it, it's fine. Just make sure you get the tools and any needed credentials inside the pod. Ideally, through the credentials should come through a secret, so they don't leak. And then you can get data in and out of Kubernetes any way you want. Of course, keep keeping the data inside the Kubernetes cluster as long as you can is probably the most efficient. So if you have hundreds, thousands, tens of thousands of pods, share the data between those pods on a resource that is inside the cluster, in this case, Ceph. And only when you are done, or before you start, because you want to pre-populate the data, get it in and out of the Kubernetes cluster. So that's it for my lecture. As usual, not too long. I believe that doing it in a hands-on session, it's much more effective. And there is the next one, which is number 3. Actually, let me share my screen so it looks better. Yeah, please. Okay. So the next one is 3A, storage hands-on. We will go over how exercising both ephemeral and persistent storage, and yeah, go over it. And as usual, if you have any questions, feel free to post them in the chat. Okay, so I hope you got a feel about the storage tool. So let's now spend a couple more minutes to talk about how resource scheduling works in Kubernetes in a little bit more detail. So in case there was any doubt, I want to make sure you understand why we need scheduling in Kubernetes. And it comes to the fact that we have lots of pods and only a limited amount of resources. And every pod will have some needs. It will need some memory, probably use some disk, some CPU, and maybe some GPUs too. In our cluster, we have GPUs. But the system, on the other hand, has a finite number of resources to offer. And while some resources can be shared, like CPUs, others cannot. A memory, it's needed. If it's used by one application, cannot be used by another. And this is where scheduling comes in. Scheduling is what finds the needed resources for the pods. So let's go more into the details what this means. All pods will have some requirements. And even if you don't specify it, you will need at least something. And in most Kubernetes clusters, if you don't specify any requirements, some defaults will be put in place. In our tutorial cluster, actually, you need to put requirements, or our API server will reject the request. Moreover, you should be aware that for most pods, the amount of resources you need will change in time. Very few applications have a constant resource need. So there is a little bit of a conundrum of what exactly your request, is it the minimum, the maximum, stuff like that. We'll go a little bit into detail in a second. But I would like to point out that some requests are critical. So for example, if I need a GPU and I know I will use 64 gigabytes of RAM at one point in time, well, I better request them or my job will not complete. But other will be preferences. For example, I'd rather use a faster CPU, but if I get a slower one, oh well, I'll live with it. Or I'm moving data across the network, and if I get the really fast network interface, I will be really happy. But if you give me a slower one, it will just take longer and I will survive. So here is an example of requirements. Down here, we have the requests. I need 1 CPU, 12 gigs of memory, and 1 GPU. And moreover, I absolutely need a 100 gigabit NIC. And if I don't need, if there are no nodes with all of these characteristics, my pod will not start. It will just sit there waiting for a resource to become available that can meet all of my requirements. On the other hand, I may request less and just put some additional limits. So in this case, I'm just asking for 12 gigs of memory, 16 gigs, but I said the limit is 16 gigs. Why would I want to do that? Well, I know that my application really doesn't need more than 12 gigs at any point in time. But if I request more, I'll probably can make good use of the disk caching that is backed by that memory. So that I still want to tell the system that would be great. And limits are not used during scheduling. If only 12 gigs available, 12 gigs will be all you will get. But this adds an additional precaution. So if my application actually is my application will be allowed to go over 12 gigs of memory. But if I ever hit 16, I'll be killed. Similarly, for CPU, if I request more CPU, then I put a limit that is higher than the request, I will be allowed to go up to the limit, but at that point, I will be throttled. So this is how you manage my resources are not fixed during the lifetime of the pod. And here, instead, we have an example of preferences. These are not hard requests, just says, I would prefer to do something compared to the other. In this case, we are talking about GPUs. And I said, well, I want a GPU. I need it. I said I need it. But if you can find me something better than these two, I would be much happier. However, if this is the only thing that is left in the system, I'm still willing to use it. It may go slower, but I will still complete my compute, and it's better than wait forever for something better to show up. Now, those are discrete requests, but sometimes you get into a situation where you have more requested resources, and in those cases, distinguishing different types of workloads can be useful. And for our purposes, we can think of the workloads that run in a Kubernetes cluster as 4 categories. You have the system pods that will often need elevated privileges, may need special resources, and they are really high priority, and they don't want to wait. If I need a service that will provide me support for the storage, well, it better runs, or nothing else in the system will work. That's the most extreme one, but there are many other system services, from monitoring to auditing and stuff like that, that you really want to run. So you want them to be at high priority. Then you have the, I would call, normal pods. They have no special privileges. They are probably long running. So if it takes a few minutes for them to start because they have to wait for a resource to come available, well, that's fine. It's, in the big picture, it will not make a huge difference. Then we have interactive pods, where people are really eager to get those resources because they're waiting for a pod to start to actually do something. So those ones should be higher priority than normal pods, because you don't want to waste human time while you wait on compute to start for you. But on the other hand, it's interactive. So people may start them and may want to go away, and you don't want to waste resources. So you may be willing to terminate them automatically if they're inactive. But in order for people to come back and continue, you want some persistence. And finally, there are opportunistic pods, often called also high throughput computing pods, where you really don't have a deadline. You have way more needs than there are compute available. So you are willing to be as flexible as possible to get as many resources as possible, which typically implies that you are willing to also go away sooner than you were expecting because a higher priority job came in. So we would like to treat these 4 types of pods separately. So how do we do that? Now, in Kubernetes, the scheduler is decent, but it's not really great because there is really no fair share notion. In case of congestion, you basically have FIFO policy, the scheduling policy, which really works best in resource-rich environments. But priorities can help with pod classes. For example, you can have a higher priority for interactive pods than opportunistic pods. So the interactive pods start sooner than opportunistic one. And similarly, you want to have a higher priority for system pods than normal user pods. And Kubernetes also allows for priority-based preemption. So that way, lower priority pods can go away fast without, but they can keep using the resources whenever there are no higher priority pods. That's really the only way to keep resources utilized 100% of the time without incurring excessive wait times for the higher priority pods. And finally, there is a notion of tolerations in Kubernetes. So you can mark certain nodes as reserved for special users or special types of workloads. And by default, normal pods will not match there. Only if you have a pod that is explicitly marked as I need or want to use those resources, will the pod be scheduled there? And you typically limit who can ask for those tolerations in order to limit it to really just the workloads they are there, and either minimize the disruption a rough pod could do, or increase startup times. So here is an example of a priority. So by default, there are no priority classes in a Kubernetes cluster, but they can be created by your admin. And we have an opportunistic priority class in our cluster. So all you need to do if you want to have the opportunistic pod in our cluster, it adds priority class, it's opportunistic. And we have some priority classes for system resources that you would not have access to, that we use for system pods. And here is an example of tolerations. You use a syntax like this. You said, well, I'm a special user. I want to be able to go to nodes that are marked as cache nodes, and normal users usually would not be able to get there, but I want to go there. And if you have the permission, Kubernetes will do that for you. So that's all from a lecture point of view. As usual, now it's hands-on time. Let me quickly share the page. Share, please. Okay. And with it's the next hands-on session, which is number 4, scheduling hands-on. Very similar to the previous ones. Just follow the instructions, and hopefully it will all work. And if not, ask questions in the chat. So off we go. So I'd like to spend a couple of minutes talking about how you actually monitor what's going on with your jobs, with the system, and stuff like that. You sort of kind of did some of that already in your hands-on exercises, but I want to put it in a couple of slides just for completion. So when you work with any system, you want to understand what's going on. And the most useful thing to know is, did I actually submit something? What happened to what I submitted? And kubectl get pods, it's what usually will use to see what requests do you have in the system, and you have used that in your hands-on already. I suggested also that you use -o wide. That provides you more information about what's going on, because without anything, you just know if it's running or not. With -o wide tells you a little more details, like where is it running, what it is IP, and stuff like that. There are more options. If you want to see the gory details, you do -o YAML, but that gets you into the expert territory, and I don't want to go there. Just be aware that you may have some controllers too, and you want to be aware of those. So you are not surprised if you delete a pod and a new one appears out of nowhere. So you have the equivalent kubectl get deployments, kubectl get jobs, and so on. And also don't forget that you may have storage too, and for that you have kubectl get PVC. But knowing what you have there, it's only part of the equation, because sometimes things just don't go as expected. And the best way to figure out why things are not going the way you think they should go is by looking at namespace events. So if you run kubectl get events, it will tell you everything that was going on in that namespace in the last, I don't remember how long is the retention. It's not very long, but in the past few minutes for sure. Just be aware that the sorting is a little weird. It's not chronologically sorted by default. So you probably want to add -- sort by meta creation timestamp. I know it's long, but that's how it is. And that will sort it chronologically. So you will see at the bottom what happened at the end. And finally, and we've done that extensively hands-on, you may want to log into your pods because you want to see what's going on, mostly for debugging, although it can be helpful for interactive pods too. If you don't specify anything, it will just run the command that you put as the last argument in the line. But if you want to make it interactive, you must add -it, and then you usually start a shell to actually log in. And finally, you may want to fetch what's going on with the standard output of whatever is running in the pod. If you instrument your application right, which means that it will print out progress on standard output, you can use fetch kubectl logs to fetch any output that was produced at runtime and see how the application is progressing. Now, you can also monitor how well your resources are being used. For our toy pods, not very useful because they are not doing anything most of the time. But if you are doing some serious compute, you want them to use as many resources as you requested, and you can use kubectl top pods to see how much CPU and how much memory is being used. And there is a similar command to actually see what's going on all the nodes. It may be a little less interesting, but especially if your application is going slower than you think it should be, if you see that that node is overloaded, it may be a good indication that maybe you have some bad players in the other pods. As I said, limits can be higher than requests, so there can start, when that happens, you can have interference between different pods. Oops. Now, that's the vanilla stuff that you get in all the clusters. Most clusters will have cluster-specific tools that provide you a much richer interface. Here in our cluster, we use Grafana to monitor what's going on. So you can see a time lapse of all the relevant attributes. But depending on which cluster you use, you will have different things. I know that the Google Kubernetes has a completely different set of GUI things. They're very useful, but very different. So that's all I have for this. And I don't have any hands-on for this session. So I'll just move on to the next slide set. Just give me a second. Let's share this. There we go. So you have seen the basics of how to run applications like they were batch jobs. Let's see what else you can do in Kubernetes that you would probably not think about when you are running in pure batch mode. So when you are a batch user, you typically don't think much about the networking. At best, you may rely on outgoing TCP connections to move data in and out. However, Kubernetes has a much richer set of networking options, and this stems from the fact that it was designed with service applications in mind, and using it for batch-style compute is actually just a nice bonus, although that's exactly what we have been trying to do most of the time. However, all this networking can actually come handy for science users too, and that's especially true for interactive applications. But science compute can make good use of it too for stuff like user portal, task queues, databases, any kind of automation. So let's spend a couple of minutes to figure out what's actually available and possible. So we sort of went over this one already. The fact that each container gets its own private IP address, which means that it's really easy to communicate between different pods, no matter where they live inside the Kubernetes cluster. The only slightly annoying thing is that every time you start a new container, actually, I'm not sure if it's container or pod, you get a new IP, which is completely non-deterministic. It may be sort of deterministic in certain clusters, but in principle, you don't know what IP will be until your pod is started. So you have to have, you would need to have some secondary channel to figure out where those IPs are in order to talk to each other. In general, pods don't have incoming networking from the wide area network, which means from outside the Kubernetes by default. Incoming. You have outgoing, typically, although, as you know, firewalls can be a problem anywhere. But typically you don't. That said, for the incoming networking, you can actually create a tunnel from your laptop using kubectl by using port forwarding, a little bit like you would do with SSH. And we have a hands-on exercise for that. And that can be really handy for interactive session when, for example, if you want to use Jupyter, which is a web-based application. Here is a screenshot of what I did from my web browser in my laptop, and I'm showing the terminal page of Jupyter. You know, you can run Python on it or stuff like that, but you can also run a terminal. And you see this is actually showing that this Jupyter is actually running inside one of the containers, even though the browser is running on my laptop. But while that is useful for interactive use, if you want to do something a little more automated, you want additional bells and whistles. And here is where the service network objects come handy. A service object essentially create a permanent name with a that can be that is associated with a permanent IP address, at least for the life of the service. So you can send traffic to that service IP, and it will be routed to any number of pods that that service is serving. There are several routing policies available. They found it round robin based on label matching, and you can Google it up and for gory detail. But from most of the time, it's very simple. You create a set of pods with a specific label, create a service in front of them, and then you can talk through the service to any of the pods behind it. It can be one, it can be many. And here is an example of how we create a service. And you see, you say service, give it a name. You will be targeting port 80, and anything that has this label will be mapped. But that only covers traffic inside the Kubernetes cluster. So let's say you want to create something inside the cluster and have pods talk to it. That was great. But what if you want to talk to it from outside, for example, from your laptop? The service object by itself is not enough. You need an additional thing that will route traffic from outside. There are two, well, the most popular abstraction is the ingress object, which is specialized for HTTP because, as you may know, HTTP it's used for everything these days. So ingress will operate straight on the HTTP application layer, and it's very flexible. It's rule-based. You can do all kinds of stuff. However, if you have an application that would be considered legacy, which means doesn't talk HTTP, there are other services that can actually allow you to have incoming connectivity to any arbitrary port on any arbitrary protocol. And we have metal LB in our cluster, but that's more advanced topics. And I just want you to be aware of it, but we will not go in any detail about it. So here is an example of ingress, and we will create a DNS name, test service at NRP Nautilus IO, and any traffic that goes there will be routed to the service named my service. As simple as that. And we will do some of that in the hands-on exercise. And that's the end of the slides. We now go back to the hands-on session. And I think it's session number 6. Let me share my screen again. Oh, oops. What happens here? Yeah. Share. It's a flow. Okay. Share. Okay. So we go again to the hands-on session. And yeah, it's number 6, networking hands-on. And yep, go over it as before. This is actually the last hands-on session, just so you know. We are at the end of the hands-on sessions, and I hope you got a taste of what's possible in Kubernetes. And I'll just have a couple more slides to give you a hint of what we didn't cover, although I'm sure there is way more than I can show in a couple of slides. But here are a couple of the things anyway. So you have seen that Kubernetes, it's quite powerful by itself, but I think it's not an exceptional system. It's really what is so great about Kubernetes is the surrounding ecosystem that really makes it so valuable, because Kubernetes has become the de facto industry standard. So there are so many projects that build on top of it to deliver additional capabilities that core Kubernetes doesn't support. And there are very few other system software that can claim that. I will mention a couple of such add-ons that you may be interested in, but that is by no means an exhaustive list. It's really just barely scratching the surface. First, I'd like to mention the Helm package manager. If you do anything that is not trivial or just a regular bad job, you may need several components in order to have your application properly working. In that case, having something that aggregates and cross-configure the various things, it's very desirable. And that's what Helm is. It's the de facto standard in Kubernetes. Most larger applications rely on Helm when they want to deploy something in Kubernetes that is complicated. And it's one of the reasons is that it's made in such a way that it uses no special privileges in order for it to use it, completely user space, and just builds on top of standard Kubernetes objects. Moreover, sorry, it has something equivalent to Docker Hub, but for Helm, they call it Artifact Hub. It's really the equivalent of Docker Hub, but for Helm decor charts. Essentially, the recipes to deploy applications through Helm, and all the major applications that need anything that is not trivial will have something in here. So something to consider if you end up building an application itself, but even if you want to just deploy something like Postgres, you just fetch the Helm charts and will make your life much easier. The other thing that is useful for many science users is Jupyter Hub. You've seen it's not that hard to create a Jupyter notebook in a pod by hand, but if you want to do it on a regular basis, it's a little annoying. So Jupyter Hub, it's essentially a web portal that an admin can install that will allow a user to go there, and that will spawn for the users the Jupyter notebook, so they don't need to manually launch the pods and then start Jupyter in them. It's not something a regular user usually would do. We actually have one instance of it in Nautilus, but since this was a Kubernetes cluster, I wanted to show how it works under the hood. But it likely in a production cluster, you will go straight through Jupyter Hub instead of trying to launch your own notebooks by hand, although you can always do that to circumvent any limitations that the hub has. And finally, since this is supercomputing center tutorial, what about MPI jobs? We didn't have any MPI jobs in our hands-on, and for good reason. Kubernetes simply does not natively support MPI jobs or gang scheduling in general. It's optimized for single node applications and very loosely coupled microservices that talk to each other. And for that, you have Helm. That said, there are several external projects that help getting a cluster to support them. Here are two that are relatively popular. There is Kube Open MPI, which will automate the MPI setup for you, like exchange SSH keys and stuff like that. And then there is the Volcano pod scheduler that allows gang scheduling, which means essentially all or nothing scheduling instead of trying to start one pod at a time. I don't think either is completely mature yet or very widely deployed, but it does provide many of the features that you would need in order to run MPI jobs. And finally, if you don't like YAML and pods, and you don't want to natively interact with Kubernetes, it is relatively easy to create an overlaid true batch system on top of Kubernetes, because Kubernetes capability are really a superset of what most batch systems provide, modulo the flexibility of scheduling. From my part, I have plenty of experience using htcondor for that. So I would deploy htcondor worker nodes inside Kubernetes and have create essentially a Condor pool out of Kubernetes resources, and users never see Kubernetes and just use Condor using the standard pilot concept. I even have a paper about that if you are interested. Not saying you should do that, but be aware that it is an option. So that pretty much concludes our tutorial. I don't have more material. Just a reminder that all the slides are in the same GitHub repo that you have been using for the hands-on. So feel free to review all the material there. They're all in PowerPoint format, but hopefully everybody these days can read PowerPoints one way or another. And the hands-on is still there. The tutorial will you will have access to your tutorial Kubernetes cluster for a few more hours at least. So feel free to finish your exercises or experiment with other stuff you're interested in. Please don't try to take over the whole cluster. It's a shared resource. But apart from that, feel free to do anything malicious on it. But yeah, that's the end. Hopefully this session tutorial was useful and you learned a little bit. But yep, that's it. Thank you.